Hi everyone, I'm Bethena Balanon and I'm an incoming college freshman from the Philippines. In this presentation, I will be summarizing our work, sharing my overall Talaria experience as well as my final thoughts about the program. To start, my research study is titled Ab Initio Analysis of TpPa-1 and TpPa-SO3H Covalent Organic Frameworks for Desalination Purposes. This study was done through the guidance of my mentor, Dr. Laura de Souza Oliveira, and one of her PhD students named Alatea Davis from the University of Wyoming. As we know, the planet we live in today has a population that is exponentially growing through the years. This then led to limited water available that is suitable for human consumption and use. Desalination, or the removal of mineral components from water, has been considered since almost 97% of Earth's overall supply is saline. Specifically, reverse osmosis is a technique being looked into. However, better membranes that have better properties can reduce overall energy use and capital costs are needed. COFs, or covalent organic frameworks, then come into the picture. But what are COFs? Well, a COF is a nanomaterial built by strong covalent forces with highly ordered channels and polar surfaces. They have prevailing properties such as thermal stability that makes them interesting to study. For this research, though, we focus on TpPa-1 and TpPa-SO3H since there have been past studies that mention their probable use in desalination. Unfortunately, this concept was only discovered in 2005, which makes it fairly new. However, it also opens up many opportunities for research. The guy in the right is actually the first person to study it, which is Professor Yagi, which is a faculty in the University of Berkeley. So the processes involved are the following. So the main objective, is to analyze TpPa-1 and TpPa-SO3H using the DFTB software to gain insights into the total charge distribution and other properties that are significant for desalination. So the processes involved are the following. So we collected respective files for the COFs from their known GitHub repositories. After that, we were able to use the DFTB Plus software to do self-consistent charge and static calculations, as well as geometry optimization. Then we did a wave plot analysis to visualize the important properties. So as seen in the slide, the Oviedo-generated figures show that the two COFs are similar to each other. The COFs are here in figure 1. So A is TpPa-1 and B is TpPa-SO3H. Their only difference is basically this the picture in B has a functionalized sulfonic acid, and you can see this because there's different big sulfur atoms in the picture. As for the self-consistent charge simulation, we first use a large separation value such as 30 to relax the molecule and optimize the geometry. So basically, we are placing the molecule inside a box and relaxing it following periodic boundary conditions. After that, we did static calculations wherein we collected the total electronic and repulsive energies. We graphed the total energy and observed the value wherein there is a significant dip in accordance to the Hohenberg-Kohn theorem. This dip corresponds to the optimal distance between the layers wherein the molecule is most stable. So here in figure 2, you can see the dip, and this is for TpPa-1, which we found at z equals 3. While for TpPa-SO3H, we found it at a value of 5. However, these values are only estimated and not exact. So we also did another geometry optimization calculation to discover the exact location of the molecules in space. And we found it at z values were of 2.7032 angstroms for TpPa-1 and 5.3919 for TpPa-SO3H. Next, wave plot was used to calculate the data needed to discover the molecule's properties, most specifically their total charge distribution. Unfortunately, we were not able to do this for TpPa-SO3H due to technical errors. However, the one for TpPa-1 is seen in the screen. And you can observe here in the picture that there are specks of dark blue and red. The dark blue represents a positive net population, while the red represents negative net population. And what population is basically electrons. So a positive net population is an accumulation of electrons, which is basically negative charge. And this can be expected within the atoms of oxygen and nitrogen because they are more electronegative than carbon and hydrogen. So what are the implications of this study? So the data we collected can be used to assess NaCl rejection and water permeance of desalination properties, I mean experiments. So to conclude, using DFTB, calculations were done to TpPa-1 and TpPa-SO3H covalent organic frameworks. Exact optimized layer separation values were then derived using the graph total energy, and using wave plot, resulting charge density distributions were calculated and visualized using OVITO. The study becomes an important step in order to study more details regarding the application of COFs to desalination and for other purposes. This is because the interaction between the COF and the ions present in water can be predicted. And some examples of future studies that can benefit from this would be those about adsorption experiments and applied machine learning. So here, the next portion will be my Talaria experience. So my mentor, Dr. Oliveira, is a chemistry professor in her university specializing on computational strategies for material development. So our project mainly used those concepts to the application for environmental sustainability. So the PhD student here in the picture is Alatea, and she helped us with my project because her thesis is very related to my topic. And they were nice enough to include me in their team website, and even now it's still there. So some details about our pairing. Me and my mentor were 14 hours apart. She was Mountain Standard Time and I was Philippine Standard Time. So we had our meetings at 8 a.m. for me and 6 p.m. for them. Next, I had a large learning curve because I didn't know anything about the topic. They were very patient with me because I really didn't know anything. And we had this like one-on-one sessions wherein they teach me about the topic. So next, the access to resources. So luckily, they gave me the opportunity to access their data cluster, which is like their computers in their university. And she also gave me the access to her doctoral dissertation because it also focused on the topic we were handling. Final thoughts. So overall, it was a very memorable experience. It was very educational and eye-opening, and it made me more interested in academia because honestly, I was very confused because I'm in college, so I should know something like what occupation I should have, but I was still very confused. And it was a great networking opportunities. So thank you very much, Athena and Romanus, Wisdom, for organizing this event. Thank you.
Oh my God, these presentations are so cool. So I have one question for you.
Sure.
It's really simple. Don't worry. I'm not going to throw you under the bus. But if you were to suggest us one thing we would do differently, what would it be?
For the research, like the topic.
Yeah.
Is that it?
Yeah.
We weren't. I think we to look more into the COFs to be used because we had TpPa-1 and TpPa-SO3H, but there are a lot of other COFs that are like more suitable, I think, or just less studied. So I think it will be interesting to look more into those and also apply machine learning. It was because of time that we didn't finish it, but we were planning to use machine learning to predict the interaction between the COFs and ions. So maybe someone else can do that.
That sounds very interesting. I'm glad you really enjoyed the experience of working with mentors. Your mentors sound really awesome. So I'm really glad you got to work with them. Good job. The next person.
Thank you.
Are you ready?
Yes, I'm ready. Can you see my screen? Okay, so hi everyone. My name is Teresa Charlene Budi Harjo. I am an 11th grader from Indonesia, and I have a big interest in sustainability and environmental technologies. In the Talaria research program, I did a research on byproduct utilization from oxy-fuel combustion. I was mentored by Sarah Bean Sherman, Science Education Specialist in the Earth, Ocean, and Atmospheric Sciences Department at the University of British Columbia. In my presentation, I will be sharing more about my research results, which is regarding one of the three methods of carbon capture and storage, oxy-fuel combustion, including its processes and financial demands. And afterward, I will be explaining a bit about carbon dioxide separation and utilization. So, when we think about death risk, we think about chronic illnesses, murders, or natural disasters. But what about climate change, the phenomenon linked to more than 5 million deaths annually? That number is scary, don't you think? But it is growing, and it will keep on growing if we do not take action to fight climate change. Carbon dioxide levels are continuously increasing, causing the Earth's average temperature to rise. These levels are even higher than it was in the past 8,000 years, with the annual increase rate being 100 times faster than the previous. More than half of that carbon dioxide gas is emitted from fuel combustion in industrial facilities, power plants, and many more devices. That's why carbon capture and storage is an important strategy in climate mitigation. Generally, carbon capture and storage refers to capturing carbon dioxide by generating a CO2-rich airstream, separating the CO2 from a flue gas, and transforming it for utilization into other commodities. Carbon capture and storage has the potential to reduce carbon dioxide concentrations in the atmosphere. There are three methods of carbon capture and storage, which are oxy-fuel combustion, pre-combustion capture, and post-combustion capture. In this presentation, I'm going to continue on particularly about oxy-fuel combustion. So, oxy-fuel combustion is fuel combustion with oxygen diluted with recycled flue gas to produce an airstream consisting of mainly carbon dioxide and water. There are three major processes in this method: oxygen production, oxygen production, fuel conversion process, and carbon dioxide purification and compression. In the oxygen production stage, to produce pure oxygen, which will be used in the fuel conversion process, nitrogen will be removed from the air pumped into the air separation unit. This waste nitrogen can be utilized to increase the energy efficiency of the whole power plant. In the next stage, fuel conversion, nitrogen is no longer involved in oxy-fuel combustion, as it has been removed in the first stage. Therefore, oxy-fuel combustion can produce flue gas with higher concentrations of carbon dioxide and also water. Next, the flue gas will go through a purification and compression process to remove water and other impurities. It is easier to separate carbon dioxide from flue gas generated by oxy-fuel combustion than regular combustion because of the low amount of impurities. This is possible due to the nitrogen removal in the first stage. This also makes the equipment needed for carbon dioxide separation be less expensive. Now, talking about financial demands. Unfortunately, the direct cost of an evaporative gas turbine system with oxy-fuel combustion is higher than those with chemical absorption, as shown in this table. However, oxy-fuel combustion is advantageous when it comes to its COA, or cost of carbon dioxide avoidance, as it costs less. From the oxy-fuel combustion, the flue gas will go through a separation process. There are 6 types of carbon dioxide separation technologies as appear in this diagram. But I will be talking more about the 2 most ideal methods for flue gas generated by oxy-fuel combustion, which are cryogenic distillation and membrane separation. Among all the other technologies, membrane separation is stable, clean, simple, energy-saving, and pressure-driven. This means that it has a better separation performance for airstreams with higher carbon dioxide concentrations, such as flue gas from oxy-fuel combustion. Other than that, cryogenic distillation also poses a good choice as it is effective for carbon dioxide separation from flue gas at high pressure with high carbon dioxide concentrations. After being separated, carbon dioxide can be used as a material for various productions, which could compensate for the implementation cost of oxy-fuel combustion in power plants. Carbon dioxide could be transformed into construction materials, fuel, industry gas and fluids, chemicals, plastics, new materials, and also agriculture. On average, each of these products' market size has the potential to grow to 60.5 times larger and reduce up to 12 times more greenhouse gas emissions in 2030. One of the categories with the largest market size and greenhouse gas reduction potentials comes from using carbon for cement production, whose current market size is $60 billion with the potential to grow to $400 billion by 2030. Other than that, carbon dioxide utilization for cement production currently reduces up to 20 million tons of emissions and will reduce up to 1,400 million tons of emissions by 2030. On the other hand, one of the biggest hindrances in implementing carbon dioxide utilization is the lack of research each plant for cost and energy efficient. Because of that, currently most carbon dioxide utilization is applied in small amounts. Moreover, current carbon dioxide utilization is not secure enough due to the limited market size. The financial demands for implementing carbon capture and storage plants are not economical. To effectuate this, some forms of policy support need to be put in place in order to drive the development of carbon dioxide utilization. These policies will support the product's market growth, encourage more people to invest in industries involving carbon dioxide and demand accountability from corporations emitting large amounts of gas. And lastly, the cost of carbon is also expensive, which requires carbon dioxide utilization to occur in years. There is a lot of development that means that with the correct steps, oxy-fuel combustion can be a major contributor to climate mitigation. I learned a lot from the Talaria program, and I am so grateful to have been given a chance to take part in it. My mentor is also super patient and helpful throughout the process, so it has been an amazing journey for me. Thank you, everyone.